All right. So, how are you guys doing? Doing okay? I didn't yet post the homework, but I'll do so after class today. Let's take a quick look at our progress through our schedule here. Today, I think we'll wrap up basically, excuse me, all that I want to talk about in terms of disinfection directly. Normally, the next lecture, I would kind of do more of a sort of special topics, advanced oxidation research kind of stuff. Since I have to miss class on the 26th, you'll have my graduate student will be lecturing that day. So be kind to him. That will not be online because he doesn't have the setup and everything. So he will just come here and present some slides, talk about the type of stuff that he's working on with research. It's some combination of disinfection and oxidation. So it's like UV and chlorine, stuff like that for kind of a specialty process. So given that, please, please be here for that and give him some encouragement if you don't mind. So that will be in place of me being here on the 26th, and instead what I'll do is I'll give the Flint water crisis kind of seminar lecture next time. Once we're done with today, you'll basically have everything, all the course content for the next exam. Okay, so you'll have some time to do the homework, to reflect on all that stuff. We've got a little bit of, I guess you could call filler, but tangential material that's not necessarily the quantitative stuff that you'll be tested on, more so the stuff that will have the Moodle quizzes kind of participation activities on. Okay, so with that, you'll have until the 31st to do the homework that I'll post today, so it gives you some time. Next time we'll do Flint water crisis, and today we're going to wrap up disinfection. Sound good? All right. So last time we left off, we had talked a little bit about disinfection byproducts, talked a bit about that, and went on to talk about kind of that contact time discussion, describing, okay, this equation that's going to go into our mass balance to describe the rate. This is going to include the specific coefficient between a given organism and a given disinfectant, plus the concentration of our disinfectant. And we can ultimately boil that down into some K star that's going to combine the two. So this is going to bring us to a first order decay reaction in effect. We might see it written as pseudo first order, but that's basically the point. All right, we also talked a bit about this graph, just showing that if we use different concentrations of the disinfectant, we get different results. And so that brought us here, and I'd like to give you a couple minutes to think about what it would take to solve this problem. So we've not done something exactly like this before, and because I'm not going to give you, an Excel sheet on an exam, or really expect all of you to be masters of a graphing calculator, I'm not going to give you exactly this type of program or this type of problem. But just out of curiosity, how many of you feel like with a graphing calculator you could solve a line of best fit given some data? If I were to ask you that today. A few of you? This is really, really interesting for me because it wasn't a terribly long time ago that I was in school, but I guess it has been a while now. When I was in high school, that was something we just had to do sometimes, is graph something with a graphing calculator and then do some processing. Now, by the time I was in college, I feel like I didn't have that type of assignment as often, so I think I could still do it, but then at one point my TI-83 broke, and so it's like, what do I do with the TI-89? You guys are like, wow, how old? Anybody have a TI-83? Yeah, love those. Okay, so anyway, all that aside, what we're going to do with this problem is take some data, do a bit of processing to extract the rate constant. And hopefully this will tie in a few things to see how we can make some observations in practice, in this case disinfecting poliovirus, and define that rate constant that we were just talking about. So a moment ago, we were mentioning that our overall rate of change for n, we could also describe as dn dt, will be described by a function, so negative reaction will have some k specific to the chlorine in this case and poliovirus, so specific to the disinfectant and microbe, times the concentration of our disinfectant with some dilution factor, but also depends on the number concentration of the virus here. And we're going to say that's first order, so that'll be dependent on the value of 1. We can also say that we could take a k star to be equal to this k times c to the n power. Okay, so that's kind of just what we had just covered about this whole disinfection thing, the Chick-Watson kinetics. Basically that the time and the concentration for the disinfection matter. But we can hold that concentration constant, and that'll help us out. So this problem says we've got data from HOCl disinfection, so that's our free chlorine, chlorinating the poliovirus at a concentration of 1.8 milligrams per liter. The temperature was 20 Celsius, the pH was 6, and then it says determine the rate constant of inactivation assuming the Chick-Watson model applies with an n value of 1. So that's talking about this n here is just 1. So there's enough information here that we could do a complicated chlorine problem with the chlorine equilibrium to see, okay, how much of this is HOCl, how much is OCl minus. So I'll just remind you that sometimes we'll need to pay attention to that equilibrium equation, right? The OCl minus plus H plus. The temperature and the pH are given to us in case we wanted to go that route. I'm going to simplify it for us today because we've done enough of these problems by now. So let's just assume that the way it's written, which is a little vague, let's assume we have 1.8 milligrams per liter of HOCl. It turns out if you were to check at pH 6 what proportion, it's probably going to be something like 97% anyway. So we could do that calculation. You've done that before, find the ratio and say, oh, okay, this should be about 98, 97% HOCl, and then do the molar conversion and all that, and it will be close to 1.8 milligrams per liter. So we could read this wording one way or the other. On an exam, I'll try to be very clear what I'm talking about. We're going to take this for a moment and just assume that's how much we have. And we're also going to assume that HOCl is really the only important disinfectant. Okay, so from here we've got data and we're trying to find K, right? It says determine the rate constant of inactivation, assuming all that. So the rate constant of inactivation, what they're looking for is the K here. So in this problem, we want to solve for K. We're given the data. We have all that background there. We're making a couple of assumptions. So give that a couple minutes to see if you can approach that in a manner that you could find that K. Now, I'll let you know that you like I kind of hinted at earlier, you'll need a line of best fit at some point to do this. So, but see if you can take the steps, even if it's on paper and just simply drawing out a plot. And you could plot, for example, this number per time as a starting point, right? So at time 0, we have something like 6,000. So we'd start here. So walk through it for a couple minutes and see if you can find your way to that answer. Feel free to work together. I'm going to fill up my water bottle. If you're noticing that if you plot it directly, it's not linear, then you're on a good track to realize that maybe you need it to be linear. All right, so if you take a look at this problem and you think to yourself, well, how am I going to solve for K? Well, we might start and think about, so we've got data and we've got like our equation that we could, do a mass balance from. And this, we weren't really given any information if there was some sort of reactor. So one thing we ought to assume is this is just in a batch system. I probably should have specified that, but we're not given any information about flow. It's disinfecting, it's in here, and this is what's happening over time, right? Even the time dependency probably tells us that we're probably in a batch system. Okay, so in that case, we could look at the math in terms of like a batch system, and we could look at what the data actually looks like. So if we plot the number versus time, it should probably look something like this, where it looks a bit exponential, right? And we had a question early on like, hey, is this supposed to be linear? Well, if we plot it, not really, as it is. And on the other hand, if we take a look at, what mathematically it would look like to solve this, we've seen it before. We can integrate from dn over n equals minus k star dt. Excuse me. And we can reach the ln of n over n naught equals minus k star times time. We could take that further and get it to be n equals n naught times e to the minus k star t. And that's actually probably the best description of what we're looking at right here. So this is the number concentration. We could assume maybe 1 liter or something, right? It didn't give us any volume or anything like that. We're given a number. So we'll just call that n. And we could say this plot is showing, given the Chick-Watson kinetics, should be showing n equals n naught times e to the minus k star t. Right? So that could make sense, but that still doesn't give us a way to translate from the data directly to our equation, or to our k. One thing you'll notice, though, is, with this exponent, that kind of explains the exponential change there. So to linearize it, what we ought to do is, instead of plotting the number there, we could plot the natural log of that number. Or even better yet, we might as well plot it as the natural log of n over n naught. And that's a calculation we can do on our end, right? We could put that into Excel and translate it over, plot that versus time. And if then we are essentially showing, instead of n equals something, we are showing the natural log of n over n naught equal to something as our graphical display, right? This is kind of like y equals mx plus b sort of a thing, where our y-axis is here, and the rest of the function is on the other side, right? So in this case, that would be minus k star times time. And, well, if m is the slope in what we're familiar with from algebra here, well, then k star should be the slope in this scenario. So in this case, this graph will actually start at 0. We'll notice that if we take a look at the natural log of 1 is 0, and the number that we're starting with divided by the number that we're starting with is going to be, that means 0, or it means 1, which is 0. So this plot should look approximately linear. There might be a little bit of variation with the data, and then we could make a line of best fit and then get the slope of that, and that should be our k star. How many of you were getting there? Anybody kind of saw that you needed to get to the linearization? Okay, great. So then we can take the k star and we'll find what that equals, and then divide that by the 1.8 milligrams per liter to put it back into this equation to find the k, right? So we could rewrite this to say K is equal to K star divided by the concentration. So what I'll say, we'll put in our answers here in a moment to get the answers for the equation. Okay, so I did this in Excel to kind of show you what this might look like. So here I just entered the raw data we were given. And we can plot, oh, I guess I didn't plot that, sorry. Thought I had plotted it. We could plot it. It kind of looks like what we saw on the graph right here, right? That's what it would look like. Now, from here, we can do a couple different transformations. One is just keep the x-axis as time, like normal. We'll look at that first. So you can ignore this part for the moment. And just take a look right here. What I did was I said, well, we need the natural log of n divided by n naught. So the n naught is always going to be times 0, n, right? So the way I wrote that was, let's take the natural log of that cell divided by that cell, but then I froze the frame with the dollar sign there, so that when I filled this downwards, we'd have whatever cell that we're currently looking at, 2 seconds in this case, divided by that original one. And so as we go down, we see we can fill that in, and we get our values for the natural log of n over n naught as a function of time. So this first graph, I'm going to plot time versus the n over n naught. And we get this nice linear relationship, and we get our slope to be 0.3758. And that's going to be per second. Okay? The K, the K here that's not the K star, the standard K, is going to just simply be, well, that divided by 1.8 milligrams per liter. So one thing we know about that is we're dividing by the units of milligrams per liter. So the units for K are going to be 1 over milligrams per liter times 1 over time. It actually ends up looking a lot like a second order equation, rate constant. But remember, we're talking about the pathogens, the viruses in this case themselves. Okay. And by the way, this chlorine is pretty effective against poliovirus. It happens rather quickly, as we know. Okay, so that should give us kind of the answer here. Pretty straightforward way to do that. This is just the line of best fit there. Another thing we could do if we wanted is account for that concentration with the time. And that's kind of coming from the concentration time. So we could multiply this by that concentration to the 1 power, and we'll still get a linear result, but this time the slope is going to be exactly K instead of K star, because it's the natural log versus on the x-axis here would be, we could rewrite this as K times C times T, noticing that we can combine the C and T and plot that. That would be another way to get our answer. So if we take this as our x-axis, where I just took the amount of time and multiplied it by 1.8 milligrams per liter, and we can plot that. That's over here on the right. This is not time. This is contact time. Stop. So if we plot it that way, we can see we'll get the same slope there. And in this case, I don't know why I have a addition there, but the 0.2079, that should be our answer here. So if we were to take 0.3758, divide that by 1.8. That should give us, if I'm not mistaken, that 0.208, we'll say. Can someone confirm that for me? That makes sense? Okay. Yeah, and it really doesn't matter too much. You know, it should be exactly the same either way. All right, does that make sense? Okay, so I wanted to show you this. I think this is hopefully useful to get a bigger, fuller picture of what's happening in our mass balances in these how to find a rate constant scenario, what you could actually do in a lab, and then relate it to our data here. Even if we're not going to do that regression analysis on an exam, I think having that level of understanding hopefully would be helpful. Okay, so let's talk about ultraviolet light for a little bit. Now, UV light, you've probably heard the phrase, you know, sunlight's the best disinfectant. That's not exactly true, at least not once you pass it through the Earth's atmosphere. It turns out oxygen and ozone absorb a lot of UV light. We can take a look at the solar spectrum, and in fact, I'll do that while I chat here for a moment. I've got some photos, well, some not photos, but some spectral images. Actually, not from this recent eclipse, but from an eclipse in 2017. We just kind of had a fun new toy in the lab to take a look, and we were able to collect the solar spectrum. So I'll grab that in a moment. But one thing I'll draw your attention to while I look for that is our visible light spectra. What we describe it as is if we're talking about wavelengths, we've got some distance between waves. So if particles are going to act, if light is going to act like a wave, where we have some motion like that, it's like a particle and a wave, the distance between two peaks or two troughs, that's our wavelength. We often describe that with the term lambda. So in that scenario, what we see with our eyes, so visible light, is between 400 nanometers and about 800 nanometers in terms of the spectra that we can see with our eyes. Anything below that starts getting into the UV range, and from about 300 to 400 nanometers, we get a little bit of that light from the sun. But it really is tapering off, and that's a great thing, because as soon as we get anywhere below 300 or 280 really, you're starting to get light that causes DNA to what we'll call dimerize. It causes distinct damage to DNA molecules that's direct. If you have the UV that's like a little bit below visible in what we might call UVA or UVB, that can cause damage because it's high energy light, and it tends to excite some molecules that can then sometimes react directly or create something that's like what we would call reactive oxygen species, the type of stuff we want antioxidants to fight against. Okay, and it turns out that skin pigment is literally an antioxidant. So our pigment is designed specifically to counteract the harsh UVA and UVB light. So the more skin pigment you have, the more natural antioxidants you have built into your skin, your hair, whatever is pigmented. The same would be true in our clothes. For instance, sunscreen is exactly that. We're putting on effectively a pigment, but it's only visible in the UV range. It absorbs a lot of UV light, but it's pretty transparent to visible light, so we don't have to see it. It doesn't look like we're caked in mud when we put sunscreen on. But if you could see in the ultraviolet range, it would look that way. Be like, oh, you've got mud all over you. Why'd you wipe that on your face? That's what it would look like. So when we're talking about the sunlight, here's, if it'll pull up, let me see if I will. There we go. Here's another image plotting the wavelength versus some intensity. And what you will notice is our visible range really is going from about here to around here. The UV range then is really just this sector, and it's really tailing off to a pretty small amount when it gets to the really harmful stuff. And then there's really none of it that's the extremely harmful stuff, kind of in this range. So with that, we're very thankful, especially for the ozone layer, but also just the oxygen in the atmosphere, that that type of light doesn't transmit very far through it. This happens to be, this is kind of the solar spectrum, what it was like. I think it was maybe September 2017, I think. We didn't have a full eclipse, but you could see the light intensity went down a fair bit. But overall, the spectrum looks about the same. We've got a lot of green light, so a lot of these visible colors, a pretty strong signal. The sun is quite strong. The counts here doesn't really mean much, but we see that there's just a lot of light coming through, but not, comparatively a lot smaller, a lot lower amount of UV light. Okay, so back to the slides then. This UVC stuff, this is the germicidal. So when we get down to there, this is what we can use to destroy viruses and bacteria, or rather really damage their DNA. If you were out in space, you would have a lot of that coming from the sun. There's no atmosphere blocking it. There's no atmosphere absorbing it, going through photochemical reactions. So if you happen to be doing a spacewalk and you somehow exposed your skin to the sunlight, that actually could be a big problem for you. Now, in addition to whatever other problems you'd have with being exposed out in space, because there's no atmosphere to block all that harmful radiation. Okay, so that's the kind of stuff we want to use in our disinfection. So the kind of the standard or conventional practice for many years has been using essentially mercury fluorescent lamps. It turns out they're very similar to the fluorescent lamps we have here. They essentially excite mercury, and so the lamps we have here have mercury vapor in them, which is why if you're disposing of fluorescent lamps of any sort, you generally should not just throw them away or just like break them or whatever. It'd be much better to dispose of them in a facility that's going to actually capture that mercury, because mercury is toxic. So if you ever do break a bunch of light bulbs on accident or something, might want to clear the area till the vapor can dissipate. At any rate, the mercury vapor inside there presumably is closed off, and when we excite it with electricity, it will give off photons in a very particular manner that will match up with the germicidal spectrum pretty well. The kind we have in our bulbs here are coated in such a way, and the plastic, underneath it and all that, that's going to block all the UV, and they're just actually using that UV photon to then excite this white coating to then do a secondary fluorescence to give us the visible light that we have in the room. There's a few challenges here. One is, how do you protect the lamp from the water flowing by? As soon as that lamp's surface gets junk on it, you would have to clean it, and you don't want to clean that the lamp directly if you can help it, because it could break. And you've got an expensive lamp that's got mercury in it that just broke. So in practice, what we do is we use a quartz sleeve, and it has to be quartz because regular glass would just absorb all the UV. So we have this fancy, fragile, expensive sleeve to protect the lamp, because the lamp is also fancy, fragile, and expensive. And so in most cases, we have water flowing through a system like this, maybe in that direction, could be the other way, we'll have some sort of quartz sleeve to protect the lamp and transmit UV. So there is a pretty large expense because I mentioned cleaning the bulb itself is not really practical. Well, you have to clean that quartz sleeve eventually because it will just get caked up with organic matter that's going through the water, with mineral deposits, with all that UV, the light. There's going to be some temperature difference, a lot of reactions happening. So it does get caked up, and then it will block light from going through it. So they do have to be cleaned every so often. Theoretically, you do that without breaking it, but it's fragile, and there's not some one set way to do this or a particular way that it's manual labor. You have to usually withdraw these units from an active water treatment process. So there's a lot of opportunities to break them, let's say. So operators typically have a significant expense in these protective sleeves. There's been some attempts at innovation. Some plastics get to have a little bit of transparency down at the wavelengths that we're talking about. That's not great for the wavelength we have with the standard mercury lamps. However, that might be more possible with UV LEDs, that we can select the wavelength a little better. We have LEDs these days, this is one of my active research topics, that essentially we can change the color of UV a little bit. Still in the germicidal effectiveness range, but we have more options, more opportunities for different materials to protect as a lens, or to do some other stuff. My grad student Caleb will talk a little more about that next week. So we use UV light. You may have seen it if you ever visited a lab that does some biological stuff. They might have one of these running at the lab bench to keep their workspace sterile or as clean as possible. Now, this UV light will not make its way through this glass pane because, as I mentioned, the glass absorbs very strongly at the germicidal wavelength. There's still some visible light coming out of that lamp, and everything inside here is exposed to this UV light. And if you leave it running for a very long time, the plastics will start to degrade because it's just so harsh. You'll see that just out in the environment as well. The photo bleaching and photo oxidation of plastics and paints and things is a thing that can and does happen. All right, so the germicidal curve. I've been talking about this for a while. This is the spectra that what we see with a mercury lamp. There's a couple types. At low pressure, this is kind of the more common one. It's got a big peak right here at 254 nanometers. It's very well known. That's been what's used for a very long time. Then we also have this medium pressure lamp that they just change a bit about how they load up the mercury. And so we still have a peak there in this germicidal area, and actually it's a little polychromatic. They also have this big peak over here near 315. That's not as useful for us. This, by the way, is kind of how sunlight happens, right? Sunlight's doing this number. Or maybe it'd be better to show it kind of like that. And this 360 here, by the way, is still definitely in the UV range. So we're not even at the visible range here on this plot. So germicidal effectiveness, you see this kind of gray curve here. That's approximately where DNA absorbs. Absorbs light, meaning that that's the type of photons that have the right amount of energy to excite the DNA and cause that dimerization, to cause the reaction that harms the DNA. You may or may not be familiar with this light absorption thing conceptually, but this is actually the same thing, same reason microwaves work. It's a very, very much different scale of the wavelength of the photon, but it's at the right frequency or the right wavelength to cause water molecules to absorb that photon in a way and vibrate because of it. So any water molecules or any molecules that are similar in vibrational capability will be excited by the microwave irradiation and heat up. Down here in our photon range for like visible light, UV light, the colors we see, what we're seeing is a photon dependence. And certain molecules will absorb more light than others, more light of certain wavelengths. And so what's left when you see green, it's actually absorbed most of the other photons, and what you're left seeing is the green photons emitted from the light bouncing off my shirt and hitting your eyes. So all sorts of reactions can happen when light is absorbed, but sometimes there's no real reaction. It's just that light was absorbed. So that's kind of the picture of how DNA, or where DNA is absorbing in terms of the color. So another example we can take a look at for two particular microorganisms. Here's Cryptosporidium parvum, which we've looked at already, and an MS2 bacteriophage. Mentioned that the other day with some data. The DNA absorption doesn't really matter too much what kind of DNA, because all DNA is really composed of the same base pairs and base units, just arranged differently. So DNA is just simply going to absorb light in this range, and then we can also translate that to how well is it killing something given a particular type of light. And what they did was they plotted this at relative to how effective 254 is. So the 254 light that was very common I mentioned, that's right here. And so they're just saying, well, let's take that as our standard one. So that's our kind of a standard point, and say relative to that, how effective is other light? So if you were to go lower wavelength, it gets harder and harder to apply lower wavelength because it's kind of hard to make it, and then it doesn't transmit very well through water or air. So anything kind of below here is pretty difficult to work with. But we can see that we might even have some benefit going up to about 270, 265. And then by the time we're at 300, we don't have much effectiveness. And which is why I say it's a bit of a lie to say sunlight's the best disinfectant. Sunlight in outer space may be pretty good. Or you just have to give it a lot of time. So the contact time sort of thing, the UV dose multiplied by how much time needs is important there. Okay, so I mentioned DNA, damage, dimerization stuff. Well, what's actually happening? I think the best way to look at it is if we imagine DNA as kind of a zipper type of a mechanism where you have all this data stored, and you're going to have to unzip it to then make copies to transmit that data, and then it'll close back up. Well, that's kind of always happening given some enzymes that our cells are doing, or the bacteria cells. Viruses insert themselves into some sort of a cell in order for that cell to do this exact thing on the virus and make replicants of the virus. So DNA is constantly being zipped and unzipped like a zipper. Now, if you imagine what would happen if you took some super glue and placed a drop of super glue on one side of the zipper, like just let's say it's unzipped, you place it between two prongs and then you let it dry, what's going to happen next time you try to zip or unzip? It's going to get stuck, right? You're going to be really annoyed that your, let's say your coat that is in perfect condition except the stupid zipper doesn't work. It's real frustrating, right? So the whole cell might be working, except this one spot in the DNA is not working, and it kind of ruins the whole deal. So it can no longer replicate or perform whatever particular function that DNA was coding. So that's this dimerization right here. It specifically happens when we have two thymine base pairs next to one another. That's the most likely one. You see a couple of, that's what we're showing right here. So then the enzyme that's acting as the actual zipping component gets stuck, and it can't continue. Another example here, normal DNA would be zipping or unzipping like normal, replicating, and then when it's trying to replicate and we've got this damage, it just gets stuck there. Okay, so that's essentially what UV is doing in this germicidal area. Now, the UV that we get from the sunlight primarily, that's a different thing. That's the oxidation stuff. That's creating some reactive oxidants. That's where our pigment is counteracting with antioxidants, right? Molecules that absorb either the light directly or can quench these reactive species effectively. So a bit of UVA light in the scheme of all this, if we back up a little bit, or a lot rather, sorry, a bit of UVA actually would stimulate pigment production, which then would be protective of the damage that UVA and UVB can cause. So there is maybe something to be said for some UVA being productive in telling your body to create vitamin D and pigment and all of that, but being careful not to expose yourself to too much UVB that's going to actually be causing burns and doing a lot of cell damage. Hopefully none of the UV that we are receiving is really going to cause this direct dimerization stuff that would be pretty bad. Okay, so let's talk a little bit about how we apply UV. One of the key issues is if we have particles in the water, that's going to be one of the issues that would prevent UV from working the most. So if we have a UV lamp and we've got these little particles floating around in water, well, a bacteria could just simply hide behind them, maybe hide inside them. See this little depiction here, viruses or bacteria. Another thing you might notice is if this is the type of scheme, you have photons blasting through the water, bacteria are actually a lot larger than a virus. So if we had a lot of small viruses here compared to fewer bacteria, UV light tends to do a better job against larger targets. In part, just the probability of hitting them. If you could have, let's say, 1 cubic micrometer of viruses compared to 1 cubic micrometer of bacteria, you'll have a lot more viruses and the same kind of surface area to target with the UV light. So UV light tends to do better against the larger organisms, which is actually kind of nice because viruses are pretty susceptible to chlorine. And so you could use UV light to kill the larger things that might be more protected from chlorine, like cryptosporidium. So there's some advantage there. If you damage a little bit of DNA in one organism, that could be enough. So there's a bit of a comparison there. The other thing to note is these particles in particular can cause reflection, can cause refraction, meaning just kind of scattering the light, changing the light a little bit. So particles can be a big issue. So we, just like with chlorine, we tend to try to filter out particles before we treat with UV. Okay, another aspect of dealing with light is how do we dose it? And it turns out, as we've been talking about, UV light is absorbed pretty rapidly by any oxygen that might be in the air or in the water. And if you think of looking through a glass of water or into a lake or a river or something, that first of all, you can see if it's has a lot of particles in it. Particles are scattering the light. You just can't see through it hardly at all. That's like trying to look through a glass of milk, right? There's so many particles in the milk, it's just going to stop all the light. Now, if you think about if you put a glass of coffee, if you put coffee in a glass and put that next to tea in a glass, you might think to yourself, oh, I bet we won't see through the coffee, but we will see through the tea, right? One has a lot of particles in it, the coffee typically, and the other just has the color from the molecules, right? So one is absorbing light, both absorb a lot of light, but the coffee is also scattering it with the particles. So when we want to know about the light absorption, in the T example, that's kind of what we would think about with this light attenuation here. So it turns out that different molecules absorb light and attenuate it at different amounts, just like the dye molecules, right? You could do the same thing putting a drop of food coloring in a glass, right? That's going to absorb some kind of light. So what we're interested in the UV sense is how much UV light is our water absorbing. And that's going to be a little different from the type of natural organic matter there, which is going to be one of the main contributors to this attenuation. So there's going to be some natural just from oxygen, just from the water itself absorbing some of the UV. But then, for example, we could compare two different rivers and their organic matter. So we've got the Suwannee River, natural organic matter. That just happens to be a very well-studied type of organic matter in the Suwannee River in Georgia. I don't remember what US here, which river that is, but it's some river, natural organic matter. And you can see given the same amount of the stuff, we have a difference in absorption. And if we're looking at light absorption like right here, we see, well, that's probably like a 30 or 40% increase from one to the other amount of light absorbed. So we can then describe the amount of light absorbed. You've actually done this if you've taken any sort of Gen Chem, passed light through a little cuvette, the spectrophotometer thing, measure how much color is there, essentially. What we're looking at is how much light is absorbed times how much concentration of the stuff that's doing that absorbing times the distance traveled. So this gives us a way to estimate or know the light transmittance through the water. So that's kind of on the design side of designing a UV disinfection system, is accounting for all of that to make sure that we know how much dose is our water really getting. Because the water that passes right next to the lamp is going to receive more light than the water that passes furthest away from the lamp. So in that scenario, we have to make sure that we design appropriately, maybe the right mixing, maybe enough dose. We design based on the amount of light that the least light received area is going to get. One way or the other, we need to design it accounting for all those factors. So how do we do that? Well, we're going to simplify and just kind of take it for granted that we know something about how much light is exposed, and our equations actually become almost exactly the same thing as what we were just covering with the Chick-Watson kinetics. Turns out that the amount of light and the amount of bacteria is what's going to matter, or the amount of pathogen, and time, of course, right? So if you had, when I say the amount of light, really I'm saying like the intensity of light times the amount of time that it's given. So if you just had one flash of really bright light, that might disinfect some, but that's a lot different than shining it for 10 minutes. Right? It's the same dose response kind of a thing. So we've got some fancy terms here, but the rate overall of destroying some pathogen using some wavelength of light, the lambda, we'll say that's equal to negative n to the 1 power. So this is our concentration, first order dependence, times this capital lambda. I had to look this up last time. This is capital lambda with a subscript lowercase lambda. This is just, we're going to just use this as k, essentially. This is like a k times this I would be the intensity of light. So this is going to be like the concentration. So the analogy is in our chlorine system or our chemical disinfectant, we have k times c. In this case, we have lambda times intensity. Each of these are specific to the wavelength of light. So if we did wavelength of 200, that's a lot different than 300. right? So this actually can change quite a bit. Okay, so each of these components are described here. Number of organisms, usually per 100 milliliters. Then this coefficient of specific lethality. Some organisms will be more or less resistant to UV light. So how resistant is it? What wavelength of light are we using? That's this guy, and the units are kind of interesting. They are area per joules, so meters squared per joule. And then the intensity is the intensity of the light at that particular wavelength. This would be watts per square meter. So power per area. What we'll notice when we combine all those units is we tend to pay attention to the time multiplied by the light energy being received. That gives us a wattage over some area that light is shining, which is where the square meters comes in. So it's kind of like selecting some area, shining light on it, and saying, okay, well, how much time did you give it? Here's that area. Here's the total dose. So we can consider a germicidal intensity equal to this lambda times I. So the intensity times the rate constant. This is very much like K star, right? That's kind of the analogy. So when we apply this to a system and we say, okay, we've dosed it with some amount of light, that would be what intensity did we use multiplied by how long did we expose it for. So it'd be a lot different exposing yourself to, let's say, the sunlight sitting out on a beach for 3 hours. That you could tell that would be a lot different if it's in the middle of the day compared to if you just had a full moon and you were getting the reflected sunlight, right? And it was, you have moonlight and it's coming from the sun, but it's a lot less intense, right? Would be very clear that that's going to have a much different outcome on the amount of light you received. Okay, this is kind of just summing that up. We could also call dosage as D, as the average intensity times time. So a couple ways to express that. Sometimes we'll describe that dosage as fluence. All right, so with all that, let's take a look at a problem. Here we have a company that's designing a solar-driven portable water disinfection system that's to be used by some military. The system is simply an inlet tube, a pump, a well-mixed chamber, and an outlet tube. So first thing we could do is draw this up. And given that we have tubes coming in and tubes going out and a well-mixed chamber, that should be a CSTR, right? So we would start there. It says water is pumped continuously into the chamber where it is irradiated by UV light before exiting through the outlet tube into a collection vessel. The disinfection rate constant is given for the UV light 7.8 per second. And watch the units here to see kind of what you have to do with the problem. The bacteria count in the water must be reduced by 99.9%. And because they need the unit to fit in a backpack, they require the chamber to be no larger than 2 liters. So the question is, how much water will the system be able to produce during 10 hours of sunlight? So in this scenario, they're just saying solar driven, meaning like that's the power, but then they have a lamp inside, right? So they're saying 10 hours of operation. How much water will it be able to produce? All right, so take a moment to look at that, and then I will join you and walk through that with you. So what you'll probably notice if you saw what I was writing here, I went ahead and drew it up. We've got the CSTR with the light shining in it, providing the reaction to occur. Drew most of the pieces up, and then as I sketched up the mass balance here, or the beginnings of it, we'll assume it's steady state operation. We've got some amount of water flowing in with some initial bacterial concentration. Something going out, we know that we have to have a ratio there, right? The N over N naught. We could describe that removal, that 99.9% removal means we can only have 0.001 remaining as a fraction. So that means N over N naught is 0.001. So we'll build a relationship there. And then the potentially tricky part is what's the reaction term? And I just wrote it as negative V K star times N. And here's where this problem could get a little bit more complicated, but as it's written, this is the same stuff we've been doing all semester, right? As it's written, we were given this rate constant that's got a per time unit. And what we were learning a few minutes ago is that, well, if we call this K star, that's going to be that lambda times the intensity for a given wavelength, where this is kind of acting like our K, and the intensity is sort of our concentration of light. So we don't really have to deal with any of that, but we could if I were to give you, let's say, how much light is needs to be dosed. If I give you all the other pieces and the question is what light intensity is needed, you could break that into pieces to say, oh, okay, well, I know the coefficient of specific lethality is X, and I know that we're going to treat, with this resonance time, then we can solve for these things. But this problem, really what we're after is, well, what flow rate? Really, it's actually flow rate times the volume, times the flow rate times the time to get the total water produced in 10 hours. They're really looking for a volume, but to get there, we need a flow rate. So with that in mind, we're going to try to find the Q, and we can relate that to the fact that our design will have some theta in it probably. The theta is V over Q. And so, I guess we could maybe just solve this straight for Q. Might be interesting to try that. But we do need to get it for sure in terms of N over N naught to relate it that way. So normally what I do is I just go ahead and divide everything by Q and start solving, and maybe look for a way to get it into this, or just solve it, resolve it, whatever I needed to later. I'm going to go ahead and give this a shot, just see if I can separate Q out by itself. Well, I guess that is dividing everything by Q. Anyway, we're just going to solve this like normal. This will be the simplest way. I'm going to leave it as V over Q, so it's kind of obvious what we're looking for. K star times N. We'll separate out the N's to one side, so N plus V over Q, K star times N, all that equals N naught. I'm going to divide everything by N here. We'll go ahead and get V over Q. Well, you know what? Let's multiply both sides by Q and divide both sides by that, N naught over N. So we'll get Q is equal to VK star times N over N naught, if I did that right. Yeah, I think that's correct. So we can get our equation in that form. We now know all the pieces, and we can just put that in a calculator to get the Q. That'll be in, since our volume's in liters and our rate constant is in per seconds, that'll give us liters per second. So then we just need to multiply that by the 10 hours worth of seconds. Yeah.
Where did the 1, because you took out the N, divided it?
You're right, I did this wrong. Sorry, hang on a second. it should be 1 plus, right? Because I did exactly that. So that should be, yeah, I knew something felt wrong, so thank you. So this should be V over Q times K star equals N naught over N minus 1. This, we could actually look at this. This should be 1,000 minus 1. So if we wanted to, we could just write that as 999. So I'm going to say V K star divided by this is equal to Q. So we'll say 2 liters times 7.8 per second, all divided by 999. All right, so if we put that into a calculator, we'll just do this in Excel real fast, get our answer, and call it there. So if we take 2 liters times 7.8 per second divided by 999, we're getting that many liters per second. So we're going to take that and multiply it by 10 hours times 60 minutes per hour and 60 seconds per minute. Should give us 562 liters produced over the course of 10 hours. This was 0.156. And so Q times 10 hours times 360 seconds per hour, 562, I think. Yeah. Okay. Hopefully that makes sense. Can you kind of see how you could put in the pieces of like the light intensity and all that? It's just another mass balance yet again in a different context. Sometimes we have to do something different with a K, right? Okay, so with that, we'll see you on Tuesday for the Flint water crisis.